Now let's look at another type of neural network known as convolutional neural network. To understand why we need convolutional neural networks, let's look at an analogy. How do you think a computer reads an image? Okay, consider this image. Okay, this is a New York skyline image. On the first glance, you'll see a lot of buildings and a lot of colors. Now, how does a computer process this image? The image is actually broken down into three color channels, which is red, green, and blue. All right, it reads in the form of RGB values. Now, each of these color channels are mapped to the image's pixel. Then the computer will recognize the value associated with each pixel and determine the size of the image. Now, for the black and white images, there is only one channel, but the concept is still the same. The thing is, we cannot make use of fully connected networks when it comes to convolutional neural networks. I'll tell you why. Now, consider the first input image. Okay, first image has a size about 28 into 28 into 3 pixels. And if we input this to our neural network, we'll get about 2352 weights in the first hidden layer itself. Now consider another example. Okay, let's say we have an image of 200 into 200 into 3 pixels. So the size of your first hidden layer becomes around 120,000. Now, if this is just the first hidden layer, imagine the number of neurons that you need to process an entire complex image set, right? This leads to something known as overfitting because all of the hidden layers are connected. They are massively connected. There's connection between each and every node. Because of this, we face overfitting, right? We have way too much of data. We have to use way too many neurons, which is not practical. So that's why we have something known as convolutional neural networks. Now, convolutional neural networks, like any other neural network, are made up of neurons with learnable weights and bases. So each neuron receives several inputs, it takes a weighted sum over them, and it gets passed on through some activation function and finally responds with an output. So the concept in convolution neural networks is that the neuron in a particular layer will only be connected to a small region of the layer before it. Not all the neurons will be connected in a fully connected manner, which leads to overfitting because we need way too many neurons to solve this problem. Only the regions which are significant are connected to each other. Alright, there is no full connection in convolutional neural networks. So guys, what we did so far is we discussed what a perceptron is. We discussed the different types of neural networks that are there, right? We discussed a feed-forward neural network. We discussed multi-layer perceptrons. We discussed recurrent neural networks and convolutional neural networks. I'm not going to go too much in depth with these concepts. Now, I'll be executing a demo. If you haven't understood any theoretical concept of deep learning, please let me know in the comment section. Right. Apart from this, I'll also leave a couple of links in the description box so that you understand the whole deep learning in a better way. Okay. If you want a more in-depth explanation, I'll leave a couple of links in the description box. For now, what I'm going to do is I'll be running a practical demonstration to show you what exactly deep learning does. So basically what we're going to do in this demo is we're going to predict stock prices. And like I said, stock price prediction is one of the very good applications of deep neural networks. You can easily predict the stock price of a particular stock for the next minute or the next day by using deep neural networks. Right? So that's exactly what we're going to do in this demo. Now, before I discuss the code, let me tell you a few things about our data set. Okay, the data set contains around 42,000 minutes of data ranging from April to August 2017 on 500 stocks as well as the total S&P 500 index price. So the index and stocks are arranged in a wide format. So this is my data set, data underscore stocks. It's in the CSV format. So what I'm going to do is I'm going to use the read CSV function in order to import this data set, right? This is just the path of where my data set is stored. This data set was actually cleaned and prepared, meaning that we don't have any missing stock and index prices. So the file does not contain any missing values. Now, what we're going to do first is we'll drop the date variable. We have a variable known as date, which is not really necessary in predicting our outcome over here. So that's exactly what I'm doing here. I'm just dropping the date variable. So here I'm just checking the dimensions of the data set, right? This is pretty understandable. You're using the shape function to do that. Now, always you make the data as a NumPy array, right? This makes computation much easier. The next process is the data splicing. I've already discussed data splicing with y'all. Here we're just preparing the training and the testing data. So the training data will contain 80% of the total data set. Okay, and also we are not shuffling the data set. We're just slicing the data set sequentially, right? That's why we have a test start and the test end variable. In sequence itself, we're selecting the data. There's no need of shuffling this data set, right? These are stock prices. It does not make sense to shuffle this data. Now, the next step we're going to do is we're going to scale the data. Now, scaling data and data normalization is one of the most important steps. All right, you cannot miss this step. I already mentioned earlier what normalization and scaling is. Now, most neural networks benefit from scaling inputs. This is because most common activation functions of the network's neurons, such as TANH and sigmoid, TANH and sigmoid are basically activation functions, and these are defined in the range of -1 to 1 or 0 and 1. So that's why scaling is an important thing in deep neural networks. For scaling, again, we'll use the min-max scaler. All right, so we're just importing that function over here. And also, one point to note is that you have to be very cautious about what part of data you're scaling and when you're doing it. A very common mistake is to scale the whole data set before training and test splits are being applied. All right, so before data splicing itself, you shouldn't be scaling your data. Now, this is a mistake because scaling invokes the calculation of statistics. For example, minimum or maximum range of the variable gets affected. So, when performing time series forecasting in real life, you do not have information from future observations at the time of forecasting. That's why calculation of scaling statistics has to be conducted on training data, and only then it has to be applied to the test data. Otherwise, you're basically using the future information at the time of forecasting, which is obviously going to lead to biasness, right? So that's why you need to make sure you do scaling very accurately. So basically what we're doing is the number of features in the training data are stored in a variable known as n stocks. After this, we'll import the infamous TensorFlow. So guys, TensorFlow is actually a very good piece of software, and it is currently the leading deep learning and neural network computation framework. Right? It is based on a C++ low level backend, but it's usually controlled through Python. So TensorFlow actually operates as a graphical representation of your computations. And this is important because neural networks are actually graphs of data and mathematical operations. So that's why TensorFlow is just perfect for neural networks and deep learning. So the next thing after importing the TensorFlow library is something known as placeholders. Placeholders are used to store input and target data, right? We need two placeholders in order to fit our model. So basically, X will contain the network's input, which is the stock prices of all the stocks at time t equal to t. And Y will contain the network's output, which is the stock price at time t is equal to t plus 1. Now, the shape of the X placeholder means that the inputs are a two-dimensional matrix and the outputs are a one-dimensional vector. So guys, basically the none argument indicates that at this point, we do not yet know the number of observations that will flow through the neural network. We just keep it as a flexible array for now. We will later define the variable batch size that controls the number of observations in each training batch. All right, now apart from this, we also have something known as initializers. Now, before I tell you what these initializers are, you need to understand that there's something known as variables that are used as flexible containers that are allowed to change during the execution. Weights and bias are represented as variables in order to adapt during training. I already discussed weights and bias with you earlier. Now, weights and bias is something that you need to initialize before you train the model, right? That's how we discussed it even while I was explaining neural networks to you. So here basically we make use of something known as variance scaling initializer. And for bias initializer, we make use of zeros initializers. These are some predefined functions in our TensorFlow module, right? We'll not get into the depth of those things. Now let's look at our model architecture parameters. So the next thing we have to discuss is the model architecture parameters. Now the model that we built, it consists of 4 hidden layers. For the first layer, we have assigned 1024 neurons, which is slightly more than double the size of the inputs. The subsequent hidden layers are always half the size of the previous layer, which means that in the hidden layer number 2, we'll have 512 neurons. Hidden layer 3 will have 256, and similarly, hidden layer number 4 will have 128 neurons. Now, why do we keep reducing the number of neurons as we go through each hidden layer? We do this because the number of neurons for each subsequent layer compresses the information that the network identifies in the previous layer. Of course, there are other possible network architectures that you can apply for this problem statement, but I'm trying to keep it as simple as possible because I'm introducing deep learning to you all. So I can't build a model architecture that's very complex and hard to explain. And of course, we have our output over here, which will be assigned a single neuron. Now, it is very important to understand the variable dimensions between your input, hidden, and output layers. So, as a rule of thumb in multi-layer perceptrons, the second dimension of the previous layer is the first dimension in the current layer. So, the second dimension in my first hidden layer is going to be my first dimension in my second hidden layer. Now, the reason behind this is pretty logical. It's because the output from the first hidden layer is passed on as an input to the second hidden layer. That's why the second dimension of the previous layer is the same as the first dimension of the next layer or the current layer. All right, I hope this is understandable. Now, coming to the bias dimension over here, the bias dimension is always equal to the second dimension of your current layer, meaning that you're just going to pass the number of neurons in that particular hidden layer as your dimension in your bias. So here the number of neurons are 1024. You're passing the same number as a parameter to your bias. Similarly, even for hidden layer number 2, if you see our second dimension here is n neurons underscore 2, I'm passing the same parameter over here as well. Similarly for hidden layer 3 and hidden layer number 4. Right, I hope this is understandable. Now we come to the output layer. The output layer will obviously have the output from hidden layer number 4. This is our output from hidden layer 4. That's passed as the first dimension in our output layer. And it'll finally have your end target, which is set to 1 over here. Right? This is our output. Your bias will basically have the current layer's dimension, which is end target. We're passing that same parameter over here. Now, after you define the required weight and the bias variables, the architecture of the network has to be specified. What you do is placeholders and variables need to be combined into a system of sequential matrix multiplication. So that's exactly what's happening over here. Apart from this, all the hidden layers need to be transformed, right, by using the activation function. So activation functions are important components of the network because they introduce non-linearity to the system, right? This means that high dimensional data can be dealt with the help of activation functions. Obviously, we have very high dimensional data when it comes to neural networks. We don't have a single dimension or, we don't have 2 or 3 inputs. We have thousands and thousands of inputs. So in order for a neural network to process that much of high dimensional data, we need something known as activation functions, right? That's why we make use of activation functions. Now, there are dozens of activation functions, and one of the most common one is the rectified linear unit. Rectified linear unit, RELU, is nothing but rectified linear unit, which is what we're going to be using in this model. So after you apply the transformation function to your hidden layer, you need to make sure that your output is transposed. This is followed by a very important function known as cost function. So the cost function of a network is used to generate a measure of deviation between the network's prediction and the actual observed training targets. So this is basically your actual output minus your model output. It basically calculates the error between your actual output and your predicted output. So for regression problems, the mean squared error function is commonly used, right? I have discussed MSE, mean squared error, before. So basically, we're just measuring the deviation over here, right? MSE is nothing but your deviation from your actual output. All right, that's exactly what we're doing here. So after you've computed your error, the next step is obviously to update your weight and your bias. So we have something known as the optimizers. They basically take care of all the necessary computations that are needed to adapt the network's weight and bias variables during the training phase. All right, that's exactly what's happening over here. Now, the main function of this optimizer is that it invokes something known as the gradient. Now, if you all remember, we discussed gradient before. It basically indicates the direction in which the weights and the bias have to be changed during the training in order to minimize the network's cost function or the network's error. So you need to figure out whether you need to increase the weight and the bias in order to decrease the error, or is it the other way around, right? You need to understand the relationship between your error and your weight variable. Right, that's exactly what the optimizer does. It invokes the gradient, which will give you the direction in which the weights and the bias have to be changed. Right, so now that you know what an optimizer does, in our module, we'll be using something known as the ADAM optimizer. This is one of the current default optimizers in deep learning. ADAM basically stands for Adaptive Moment Estimation, and it can be considered as a combination between very two popular optimizers called AdaGrad and RMS-Proc. Now, let's not get into the depth of the optimizers. The main agenda here is for you to understand the logic behind deep learning. We don't have to go into the functions and all. These are predefined functions which TensorFlow takes care of. Next, we have something known as initializers. Now, initializers are used to initialize the network's variables before training. We already discussed this before. Now, I defined the initializer here again. I'd already done it earlier in this session, right? Initializers are already defined. So I just removed that line of code. Next step would be fitting the neural network. So after we've defined the placeholders, the variables which are basically weights and bias, the initializers, the cost functions, and the optimizers of the network, the model has to be trained. Now, this is usually done by using the mini batch training method because we have a very huge data set, right? So it's always best to use the mini batch training method. Now, what happens during mini batch training is random data samples of any batch size are drawn from the training data and they are fed into the network. So the training data set gets divided into n divided by your batch size batches that are sequentially fed into the network. So one after the other, each of these batches will be fed into the network. At this point, the placeholders, which are your X and Y, they come into play. They store the input and the target data and present them to the network as inputs and targets. That's the main functionality of placeholders. What they do is they store the input and the target data and they provide this to the network as inputs and targets. That's exactly what your placeholders do. So let's say that a sampled data batch of X, right? Now this data batch flows through the network until it reaches the output layer. There, the TensorFlow compares the model's predictions against the actual observed targets, which is stored in Y. If you all remember, we stored our actual observed targets in Y. After this, TensorFlow will conduct something known as optimization step and it will update the network's parameters like the weight of the network and the bias. So after having updated your weight and the bias, the next batch is sampled and the process gets repeated. So this procedure will continue until all the batches have presented to the network. And one full sweep over all batches is known as an epoch. So I've defined this entire thing over here. So we are going to go through 10 epochs, meaning that all the batches are going to go through training, meaning you're going to input each batch that is X and it will flow through the network until it reaches the output layer. There what happens is TensorFlow will compare your predictions, that is basically what your model predicted, against the actual observed targets which is stored in Y. After this, TensorFlow will perform optimization wherein it'll update the network parameters like your weight and your bias. After you update the weight and the bias, the next batch will get sampled and the process will keep repeating. Right? This happens until all the batches are implemented in the network. So what I just told you was one epoch. We are going to repeat this 10 times. So our batch size is 256, meaning that we have 256 batches. So here we're going to assign X and Y, what I just spoke to you about. The mini batch training starts over here. So basically your first batch will start flowing through the network until it reaches the output layer. After this, TensorFlow will compare your model's prediction. This is where predictions happen. It will compare your model's prediction to the actual observed targets which is stored in Y. Then TensorFlow will start doing optimization and it will update the network parameters like your weight and your bias. So after you update the weight and the biases, the next batch will get input into the network and this process will keep repeating. This process will repeat 10 times because we've defined 10 epochs. Now, also during the training, we evaluate the network's predictions on the test set, which is basically the data which we haven't learned, but this data is set aside for every fifth batch, and this is visualized. So, in our problem statement, what our network is going to do is it's going to predict the stock price continuously over a time period of t plus 1. Right? We're feeding it data about the stock price at time t. It's going to give us an output of time t plus 1. Now let me run this code and let's see how close our predicted values are to the actual values. We're going to visualize this entire thing, and we've also exported this in order to combine it into a video animation, right? I'll show you what the video looks like. So now let's look at our visualization. We'll look at our output. So the orange basically shows our model's prediction. So the model quickly learns the shape and the location of the time series in the test data and showing us an accurate prediction, right? It's pretty close to the actual prediction. Now, as I'm explaining this to you, each batch is running here, right? We are at epoch 2. We have 10 epochs to go over here. So you can see that the network is actually adapting to the basic shape of the time series, and it's learning finer patterns in the data. You see, it keeps learning patterns, and the prediction is getting closer and closer after every epoch. So let's just wait till we reach epoch 10 and we complete the entire process, right? So guys, I think the predictions are pretty close. Like the pattern and the shape is learned very well by our neural network. It is actually mimicking this network. The only deviation is in the values. Apart from that, it's learning the shape of the time series data in almost the same way. The shape is exactly the same. It looks very similar to me. Now, also remember that there are a lot of ways of improving your result. You can change the design of your layers, or you can change the number of neurons. You can choose different initialization functions and activation functions. You can introduce something known as dropout layers, which basically help you to get rid of overfitting. And there's also something known as early stopping. Early stopping helps you understand where you must stop your batch training. That's also another method that you can implement for improving your model. Now, there are also different types of deep learning models that you can use for this problem. Here we use the feed forward network, which basically means that the batches will flow from left to right. Okay, so our 10 epochs are over. Now, the final thing that's getting calculated is our error, MSE or mean squared error. So, guys, don't worry about this warning, right? It's just a warning. So, our mean squared error comes down to 0.0029, which is pretty low because the target is scaled. And this means that our accuracy is pretty good. So, guys, like I mentioned, if you want to improve the accuracy of the model, you can use different schemes, you can use different initialization functions, or you can try out different transformation functions. You can use something known as dropout technique and early stopping in order to make the training phase even more better. Yeah, so guys, that was the end of our deep learning demo, right? I hope all of you understood the deep learning demo.